Most people think building AI is just writing clever code. But if you're an engineer, you know that's only half the story. Today, we're distilling Stanford's hour-long Lecture 3 into just 5 minutes to reveal the real workflow of a machine learning project, from the first line of code to continuous maintenance. We'll walk through why AI development is fundamentally different from traditional software, how experts use speed to their advantage, and why deploying a model is just the beginning of your job. The fundamental difference. AI systems are not like traditional software. In a traditional program, the developer writes code, and the system behaves exactly as instructed. The developer has full control. In an AI system, the behavior depends on both the code and the data used for training. Even if the code is perfectly designed, the model might behave differently based on patterns and variations it learned from the training data. Because of this reliance on data, machine learning is an experimental and iterative process. You don't build a perfect system from day one. Instead, developers build an initial model, analyze its performance and mistakes, and then cycle back to improve the model or the dataset. This continuous cycle is design, train, analyze, improve. The workflow and strategy. This iterative mindset drives the entire workflow of an ML project. The process begins by specifying the problem, collecting the necessary training data, and then designing and training the model architecture. To speed this process up, fast data collection is key. Instead of waiting a long time to collect a perfect dataset, it is better to collect a smaller dataset quickly and start training an early version of the model. Why? Because training an initial model reveals what problems actually exist in the system, guiding your next steps. This next step is crucial: error analysis. The face recognition example. Imagine building an AI face recognition system for office access control. The camera captures an image, the system analyzes it, and determines if the person is authorized to unlock the door. During error analysis, you might discover your system struggles to recognize people wearing hats or glasses. That insight, that specific mistake, allows you to design a system that handles those cases more efficiently. Real-world efficiency often means efficient system design using multiple stages. For example, a system may first run a simple, lightweight process like rapid prototyping to detect motion by checking for pixel changes between frames. Only when motion is confirmed is the image sent to the more complex neural network for face recognition. This design reduces unnecessary computation. The continuous challenge. Once the model is trained and performing well, it's ready for deployment into a real application, which often involves integrating it into a server or cloud platform. But the work is not over, because the real world changes. This is where data drift occurs. People might start wearing sunglasses in the summer or scarves in the winter. These differences in input data distribution can cause your system's performance to drop. To combat this, the system needs continuous monitoring after deployment. Engineers track metrics like prediction accuracy and system latency on dashboards. If performance slips, it signals the need for maintaining and updating AI systems. You must continuously collect new data, retrain the models, and improve the system to maintain its performance. AI systems, unlike traditional software, require continuous monitoring, maintenance, and improvement.